Good morning, students. Today our topic is force on current carrying conductor in a magnetic field. You know well Lorentz force. Lorentz force is nothing but the force on a charge in a magnetic field. So what is the force on charge in a magnetic field? F is equal to E into Vd vector cross B vector. If charge is negative, which means electron, so the symbol is negative. If charge is positive, plus E into Vd vector cross B vector. The force F is equal to E into Vdb sin theta, which means F is equal to the charge is Q, B field magnetic field, draft velocity Vd sin theta. So BQV sin theta is a Lorentz force. But here force on current carrying conductor in a magnetic field. Just consider one conductor, the number of electrons, I mean the free electrons, E. When current flows through the conductor, I. So force on current carrying conductor. When current flows through the conductor is I, electron E, draft velocity of electron is Vd in opposite to the direction of current. If charge is positive, just I want to take positive charge. This is current direction I. If charge is positive, I consider positive charge, draft velocity along the direction of current. So draft velocity of electron is opposite to the direction of current if charge is negative, which means consider electron. And consider positive charge. The draft velocity along the direction of current. What is the relation between draft velocity and electric current? I is equal to VDENA. Vena is not a Vena, this is Vena. I is equal to VDENA. Vd is the draft velocity of charge of electron, positive charge. If charge is negative, the symbol is negative. If charge is positive, symbol is positive. ENA, charge, this is number of electrons per unit volume. This is area of cross section of the conductor. What is the relation between draft velocity and current? I is equal to VDENA. Lorentz force of a single charge. You know well the force on a charge in a uniform magnetic field. Lorentz force F is equal to BQV sin theta, which means F is equal to E into Vd cross B vector. This is a basic one. And next one, our topic is force on current carrying conductor in a magnetic field. Force on current carrying conductor in a magnetic field. So, force on a current carrying conductor in a magnetic field is nothing but sum of the Lorentz force in individual charge carrying a wire. Total, I mean the number of electrons, which means single electron produce a Lorentz force, F is equal to E into Vd cross B vector. I want this force on current carrying conductor in a magnetic field is nothing but sum of the Lorentz force of individual charges carrying a wire. Consider uniform magnetic field. Just I want to take this uniform magnetic field. This is uniform magnetic field B. When conductor is placed in a uniform magnetic field, the length of the conductor is L. The angle between conductor and magnetic field is theta. This is AB. For A is not A. PQ is a conductor. L length of conductor placed in a magnetic field. Force on a current carrying conductor. When current flows through the conductor is I. I current flows through the conductor. Current carrying conductor placed in a magnetic field. The conductor to make an angle theta with magnetic field. So I current flows through the conductor. If charge, I consider one single electron E, draft velocity of electron is Vd. opposite to the direction of electric current. If I is equal to electric current, if charge is negative, draft velocity is opposite to the direction of electric current. Current is equal to, if charge is positive, draft velocity is along the direction of electric current. So it's very important. What is the relation between draft velocity and electric current? You know well in second lesson, I is equal to VDENA. Lorentz force F is equal to E into VD vector cross B vector. Here, total, the sum of Lorentz force in charge, sum of Lorentz force of individual charge carries a total wire or conductor. Here, I is the flow of electric current, draft velocity opposite direction of charge electric current. If charge is positive, draft velocity is along the direction of electric current. The conductor should make an angle is theta with the magnetic field B. So very important. I want to calculate this. What is the force on single electron or single charge? Force on one electron or one charge is positive. Inconvenient, I want to take this positive charge which is equal to E into VD vector cross B vector, which is equal to E into VD B sin theta. VdB sin theta, force on one charge. The force on one charge is nothing but, I want to calculate the force on a current carrying conductor in a magnetic field is nothing but sum of Lorentz force in individual charges carrying in a wire. I want to take just one single electron, force on a one charge is equal to E into Vd into B sin theta. So consider one single element in total length. I want to take in small element of the current carrying conductor dl. The area of cross section of current conductor is A. Area of cross section of current carrying conductor is A. So this is small element dl. Small element dl. I want to calculate here total number of electrons, total number of free electrons. Here N is the number of free electrons per unit volume. N is the number of free electrons per unit volume. In single volume, which means 1 unit volume, number of electron is N in unit volume. It's a very important one. See, N is a unit volume of free electrons in a unit volume. I want to calculate this total number of electrons, caps N, in given element dl. Given element dl. So total number of electrons in small element, which means small element means small current element. It is called as a current element. IDL is a current element. IDL is nothing but I is a scalar quantity. IDL is a vector quantity. This is a very important one. IDL is a vector quantity. Is called as a current element. When current flows through the DL element in a length of DL, I current flows through a DL length. So this is vector quantity. So I is scalar quantity. So number of electrons in small element caps N is equal to, I want this, it's a very important one. Small n is nothing but number of electrons per unit volume. Caps N is nothing but number of electrons in this element. Total number of electrons is this element. So which is equal to N into volume of this element. Volume of this element. So N into B. So caps N is equal to N into volume is equal to area of cross section into length. So area into length. So I want to calculate this volume of small element. So N is equal to N into V is equal to nothing but A into dl. A into dl. So small n is the number of electrons per unit volume. Caps N is the number of electrons in given current element. So next one is, I want to calculate this. What is the force in small element? What is the Lorentz force in small element in n number of free electrons? So force on a small element, force on a small element in n number of electrons, in n number of electrons is equal to n into one charge, I mean force on a one charge, one electron is equal to, I have to take small f. So f is equal to E into VdBV sin theta. So n into, if one charge, force on one charge is this. I want to calculate force on a small element. Here n number of electrons are available. So force on small element in dl, number of electrons is caps n, which is equal to n into E VdB sin theta. N into E VdB sin theta, which is equal to, this is force on small element. I want to take this df vector. Df vector is nothing but force on small element, I mean current element in dl length, which is equal to n into E VdB sin theta. What is n value? N into A dl. This is n into A dl into E VdB sin theta. So this is small element. I want to take the force on small element, I mean current element in dl length. Want to calculate in total length. Take in integral. Integral of df is equal to integral of NA dl E VdB sin theta. So df is equal to, net force F is equal to N A E VdB is a uniform constant sin theta integral of dl. So F is equal to, you know well, VdENA is nothing but, this is current I. So B sin theta integral of dl is equal to L. So F is equal to BIL sin theta, or F is equal to ILB sin theta. This is the magnitude of the force. Magnitude of force is nothing but force on current carrying conductor in a magnetic field. F is equal to ILB sin theta. So theta is nothing but angle between IL and magnetic field. F is equal to, is very important, IL vector cross B vector. IL vector cross B vector, or F vector is equal to I into L vector cross B vector. L vector cross B vector, but not possible to F vector is equal to I into B vector cross L vector is wrong one. So L vector cross B vector, because of direction is very important here. Direction is, the I want to calculate is current direction, this is a field direction. What is the force direction? The force direction gives two law. One is a palm rule, right hand palm rule, or another one is Fleming's left hand rule. Here F vector is equal to I into L vector cross B vector, or F vector is equal to IL vector cross B vector. So IL is nothing but, this is a current element. How much of current flows in dl length? This is called as a current element, IL vector. So F vector is equal to B IL sin theta. This is the magnitude of force. So F vector is equal to IL vector cross B vector. F is equal to B IL sin theta. This is the magnitude of force. I want to calculate what is the direction of force. Direction of force. And next one, see, F is equal to BIL sin theta. What happens if theta is equal to 0? In case 1, if theta is equal to 0, what happens? Theta is nothing but the angle between IL and B. So this is IL vector, is the length of the conductor. This is a field. angle between length of the conductor and field. If the length of the conductor is parallel to the field, what happen? Theta value is 0. The length of the conductor is parallel to the field. If theta is equal to 0. So theta is equal to 0 means force F is equal to BIL sin 0. F is equal to BIL sin 0 value is 0. So 0 into BIL is 0. So there is no force. In case 2, what happens if theta is equal to 90 degrees? If theta is equal to 90 degrees, the current carrying conductor is perpendicular to the magnetic field. This is the magnetic field. This is the length of the conductor is perpendicular to the magnetic field. Theta is equal to 90 degrees. So F is equal to BIL sin 90 degrees. Sin 90 is 1. The force F is equal to BIL maximum. When the conductor is perpendicular to the magnetic field, force is maximum. Parallel to the magnetic field, force is 0. Here, the force is directly proportional to magnetic field. The force is directly proportional to length. And another one is very important. F is perpendicular to the magnetic field and force is perpendicular to the length of the conductor. It is a very, very, very important one. Another one is, I want to calculate the direction of magnetic field. Direction of magnetic field and direction of force. Direction of force. Here two laws is possible. One is a right hand palm rule. Right hand palm rule is nothing but the finger is indicate direction of field, thumb points to direction of current, the palm is direction of force. For example, this is a field. This is field. Fingers indicates a magnetic field. Thumb points the direction of current. So the palm is direction of force. The palm is indicates the direction of force. This is a right hand rule. Another one is a Fleming left hand rule. What is a Fleming left hand rule? You know well. In left hand, touch the forefinger and middle finger and thumb is perpendicular to each other. The forefinger points to the direction of magnetic field and middle finger points to the direction of current and thumb is points to the direction of force. The Fleming left hand rule. Here, this is a palm rule. Most of the palm rule is a very easy one compared than Fleming left hand rule. This is a palm rule magnetic field. This is current. So this is angle is 90 degree. The force indicate the palm is indicates the direction of force. Direction of force. See this field direction. This is a field direction. This is a current direction. Force is direction of inward direction. The force is inward direction. This is very important. And Fleming left hand rule. This is field direction. This is current direction. Thumb points the direction of force. Thumb points the direction of force. Mid finger, the forefinger points the direction of field. Middle finger points the direction of current and thumb points the direction of force. Inwards direction. Force direction is inwards. So this is a force on current carrying conductor in a magnetic field. Formula is nothing but F is equal to BIL sin theta. The force is 0 when theta value is 0. The force is maximum when theta is equal to 90 degree. F is equal to BIL sin theta. The direction of force is Fleming gives the direction of force gives the Fleming left hand rule and right hand palm rule. It's a very important topic and important 5 mark question also. Next is example, find the direction of force. Consider if cross value is field is inwards. This is field is outward direction symbol. This is field is inward direction symbol. You know well. Consider magnetic field to find direction of force. This is a current carrying conductor I. What is the direction of force? This is I want to take palm rule. This is the inward direction. Magnetic field is inward direction. Current. This is how thumb points the direction of current. And palm is the direction of force. This is the direction of force. The force direction is upward. This is F. So what is this? Another one example. if field is outward direction, field is outward direction, this is inward field, this is outward field. If the wire is placed in this direction, current flows this I current. What is the direction of force? The field is outward. See, outward direction. This is outward direction. This is current direction. The finger is indicate the magnetic field. Thumb points the direction of current. What is this? Force direction. This is inward. I mean this direction. This is force direction. This is field outward direction. Simple. Field outward direction. Thumb points the direction of current. The palm is direction of force. So this is direction of force. Another one is, what is the direction of, what is the value of magnetic field? Value of magnetic field. Value of force. What to calculate the force? This is current carrying wire. I current flows through the field. The magnetic field is B. This is 30 degree. To find the force, value of force. You know value F is equal to BIL sin theta. BL sin theta. Suddenly we enter the answer BIL theta value is 30 degree. So sin 30 1 by 2 sin 30 degree. This is a wrong one. See, it's a very important. Cross means the field is inward direction. Field is inward direction. This is a current element. The force in a bomb indicates the direction of force. You know well, force is perpendicular to the conductor, current element, and the force is perpendicular to the current. It is a very important. Here, the 30 degrees indicates the plane of the magnetic field. This is plane. The magnetic field is enter. Cross means in the inward direction. The plane should make a field. But here 30 degrees now is not a magnetic field between length of the conductor and magnetic field. 30 degrees is the plane of the paper or plane of the magnetic field. So here angle between is a very important angle between current carrying element and a magnetic field. This is a magnetic field, this is current carrying element, angle is 90 degree. This is very important. So 90 degree. So correct value F is equal to BIL sin 90, value is 1. So F is equal to BIL is the correct answer. So don't put BIL sin 30 degree. It's not a angle between B and IL. This is 30 is nothing but the angle between magnetic field and plane of the paper. Plane of the magnetic field. This is a wrong one. So be careful. F is equal to BIL is a correct answer. And next one, to calculate net force. To find net force is a very important, is an easy one. Inside magnetic field is inward direction. Magnetic field is inward direction. The length of the wire is L. The flow of current is I. The point is A. Another one length of the wire is L. The flow of current is I. So the current flows this. I current flows in this direction. A to B. What is the, to find net force in a given magnetic field, given a uniform magnetic field. This is a magnetic field inward direction. I want to calculate this very easy one. See, first of all you direct the direction of force. You measure the direction of force. This is field. You know well the finger indicates the direction of field. This is thumb points the direction of current. So palm indicates the direction of force. So force direction is this. F produces the perpendicular to the field, so F is equal to BIL sin theta, theta value is 90 degrees, so F is equal to BIL. Another one, here the point is field is inward direction, thumb points the fingers indicates the direction of field, thumb points the direction of current, the palm indicates the direction of force. So here force direction is F. See, here force is in this direction, here force is, this element to produce a force is in this direction. It is very important. Should make an plane of the angle is 30 degree. The magnetic field should maintain angle is 30 degree. This is also 30 degree. What is the force? To find the net force. Here, these element produce force here in this direction. I mean this element produce the forces in this direction. To find the resultant force. Know well, one force, this is another force. Here, this is 30 degree. It's very important. 30 degree is not a angle between field and element. This is a plane. To make this is also 30 degree. So this angle is 60 degree. You know well, the force is perpendicular to the length, perpendicular to the current element, perpendicular to the field. I mean, to make an this is 30 degree and this is 60 degree. So this angle is 60 degree, this angle is 60 degree. So this is 60 degree, this force is 60 degree. This is F, this is F. To divide a free body diagram in lower section, this force produced in this vertical, horizontal, F cos 60 degree, F sin 60 degree. These forces result in two components. One is vertical component, F sin 60. Another one is F cos 60. F cos 60. So these force, this component opposite to the direction of this component. So this is equal and opposite, so negligible. The resultant force is equal to F net force is equal to 2F cos 60 degree. 2F cos 60 degree. So F net force is equal to 2 into F cos 60. What is the cos 60 value is? 1 by 2. 2 cancel. So F net force is equal to F, which is equal to BIL. BIL. This is the correct answer. So examples of force on a current carrying conductor in a magnetic field. It's a basic examples. It's a very important. This component, I mean the free body diagram means a very important role in this problem. Because of the free body diagram should to make a perfect, I mean correct component of force. If equal this component, the resultant force of components F sin theta, I mean this force component F sin 60, F sin 60 equal and opposite. So these two components not valid. So F horizontal components make an resultant force F net is equal to F BIL value. So F BIL sin theta, theta value is 90 degree. So next one, on example 3.27, a metallic rod of linear density is 0.25 kg per meter is lying horizontally on a smooth inclined plane. Horizontally on a smooth inclined plane, the metallic rod. This is a metallic rod in horizontal surface, smooth inclined plane, which makes an angle of 45 degree with horizontal surface. In horizontal surface, to make an angle is 45 degree. The rod is not allowed to slide down. It's a very important. The weight of the object is W is equal to mg. In inclined, smooth inclined plane, the object must be slide down, but the object does not slide down because of the rod is not allowed to slide down by flowing current through it when a magnetic field strength 0.25 Tesla is acting on its vertical direction. The field acts in vertical direction. The flow of current I is in the conductor, I mean the rod. By flowing current through it when a magnetic field of strength 0.25 Tesla acting in the vertical direction. Calculate the current flowing in the rod to keep it stationary, which means the object does not slide down, which means the object is stationary. So, if consider inclined plane, the rod must be slide down, but I current flows through the conductor and a vertical magnetic field, so must act in force. That force should maintain in stationary. I want to calculate how many current flows through the conductor, the object maintain stationary, keep it stationary, which means calculate the electric current flowing in the rod and keep it stationary. Just I want to take in the free body diagram. You know well in lower section, if consider the rod is just take in this direction, inclined plane. I want to consider this. This is a insert. The current flows through the direction. Consider this is inclined plane. I want to take in the free body diagram. In this path here, the conductor is placed in this direction to make an inclined plane. So now it's a 45 degree. The angle which makes angle of 45 degree horizontal. So 45 degree is a conductor. It's a very important. This is the inclined plane. The weight of the object is W is equal to mg. You know well, equal and opposite normal force act on the object is, this is normal force. So the mg is divided into two components. One is mg cos theta. Vertical component is mg sin theta. This is the weight of the object in downward direction. This is a normal force. This normal force should equal an opposite component of mg cos theta. Mg cos theta must be balanced normal force. A normal force must be balanced mg cos theta. So this component mg sin theta should slide down the rod. So mg sin theta is acting in this downward direction. But the electric current flows through the conductor. See the diagram. The I current flows through the conductor in a vertical component. See, this is a vertical component, magnetic field direction. The current flows through the conductor is this direction. What is the force direction? Just to take the figures of magnetic field direction. So this is a field direction. Very important. The finger indicates the field direction, thumb points the direction of current. So the palm indicates the direction of force. So force is acting in this direction. Force is acting in this direction. So is a very important form rule. The finger indicates the direction of field, thumb points the direction of current. So palm is indicates the direction of force. According to Fleming, left hand is a field direction. This is field direction. Forefinger points the direction of field direction. Middle finger points the direction of electric current. The thumb points the direction of force in this direction. The force. This force is divided in two components, horizontal component and a vertical component. This angle is 45 degree. You know well, so this is a 90 degree. So this is also 45 degree. This is 45 degree. The mg sin 45. This is mg cos 45. This is the resultant force F act in this direction. BIL sin 90 degree. Theta value is 90. So F is equal to BIL. So maximum. These force is divided as two components. One is F cos theta, another one is F sin theta. See, this component F sin theta component acting along the direction of a current carrying conductor. So theta value is 0. That F sin theta is, there is no, that component F sin theta component is not effect on the conductor. So F cos theta should act in this direction. This is opposite direction of mg sin theta. F is a resultant force. It's a very important FBD. FBD means a free body diagram. So F is a resultant force. This is divided in two components. One horizontal component, another one vertical component. The vertical component along the direction of the conductor. So the vertical component is not act on the conductor. So there is no value. So F cos it is a horizontal component act in this direction. These forces must to maintain stationary on inclined plane of the rod maintain stationary in inclined plane. So mg sin theta and f cos theta must be equal. If these two forces equal means the rod is not allowed to slide down. Because of the rod, keep it stationary. So I want to calculate this f cos 45. This is theta is 45 degree. So this is also 45 degree. So mg sin theta must be equal to f cos theta. If this force is equal to mg sin theta means the rod must be to maintain stationary. So mg sin theta value is 45 degree, which is equal to f cos theta value is 45 degree. mg sin 45 is equal to f is equal to bil cos 45. I want to calculate this current I value. What is I is equal to mg sin 45 divided by BL cos 45. BL cos 45. So I is equal to M value. M divided by L is a linear density. Linear density is nothing but linear density equal to mass by length. Mass by length. M by L is equal to 0.25 kilogram per meter. So linear density is nothing but mass by length. So mass by length is nothing but the linear density value is 0.25. 0.25 into Z 9.8 sin 45 divided by cos 45 is equal to tan 45. So divided by B value. B value is 0.25 Tesla. So I is equal to 0.25 cancel. So 9.8 into tan 45. Tan 45 is equal to 1. So I is equal to 9.8 ampere. If 9.8 ampere current flows through the rod must be, which means the 9.8 current flowing in the rod to keep it stationary. Which means the rod must be stationary. This is a very important problem. Practice it. Thank you.